Hi, my name is Barry Scott, and I'm a Solution Business Manager here at Keysight Technologies. For the next couple minutes, I'd like to describe to you a couple of the key challenges when you're trying to extend the battery life of your IoT device. Obviously, there's billions of IoT devices that are being deployed around the world right now. And they may be in spots that are very hard to reach. You might have a IoT device on a mountaintop that's sensing weather. You might have one that's in a very hard to reach part of an industrial warehouse that's doing humidity and temperature for that warehouse. In fact, you might even have one that's inside your body, which is really hard to reach. And so it becomes more and more important to have long battery lives so that you don't have the maintenance costs to have to replace those batteries frequently. Now, traditionally, customers will use things that they already have on their bench, things like a DMM, maybe it's an oscilloscope with a special probe, or it might be a source measurement unit to try and capture the current waveform that's coming out of the battery going into their IoT device. Now, there's two challenges with this approach. The first challenge is trying to capture that current waveform accurately. If you think about it, you've got an IoT device that has several different subcircuits that are turning on and off. For example, you've got a radio that's turning on and off. You've got a microcontroller that's going from sleep state to an active state. You might have actuators or sensors that are turning on and off as well. And that presents a couple challenges. One is, when you're in a sleep state with a microprocessor, it might only be pulling, say, hundreds of nanoamps or tens of microamps. And then when it goes full on active, it might be up in the hundreds of milliamps. And that's a lot of dynamic range and a lot of vertical resolution required to capture that waveform. And that makes it sort of a challenge for something like an oscilloscope that might only have 8 or 10 bits of resolution. You've also got the challenge of these things pulse on and off very quickly to try and conserve battery. And so with these shorter pulses, you really do need some pretty good bandwidth to be able to capture those waveforms accurately. And that might be a challenge for something like a DMM where the front end bandwidth is limited to several kHz or 10 kHz, something like that. Okay, so capturing that accurate current waveform is truly a challenge. The second major test challenge with this approach is once you've captured that waveform, it's a single composite waveform, right? So even though you've got several different subcircuits that are powering on and off and that are consuming varying amounts of charge, you only end up with one single waveform that you're left to try and understand so you can figure out where to put your effort to try and tune those subcircuits. And so, how do you break that single composite waveform down into its constituent pieces so that you can make those design decisions on your IoT device? Well, I'd like to introduce you to a new solution from Keysight. It's called the X8712 IoT Device Battery Life Optimization Solution. Now, it addresses both of those test challenges. It addresses the first one around capturing the accurate waveform because it's based on the Keysight N6705C DC power analyzer. That's this unit right behind me here. The DC power analyzer has been around for a number of years. It's fairly well known out in the industry. And when you put an N6781 SMU module into it, it gives us some phenomenal capabilities that you really can't get anywhere else. It has vertical resolution that approach an effective number of bits, roughly 28 bits, because it has a feature called seamless ranging and it's glitch free. So you really can't capture the lowest off states all the way to the highest active states on your waveform. It's also got good bandwidth so that you can capture the edges on those pulses and you can really capture an accurate waveform. And it's got a built-in digitizer, very similar to an oscilloscope in that way, so that you can capture long periods of waveform so that you can analyze those. Okay, so since we based it on the N6705C, we're able to solve that problem around capturing those accurate waveforms. The second problem around what do you do with this single composite waveform that you've got? How do you read more insight into that and know what subcircuits to tune? The way we do that is actually with some addition of hardware and software that we put on top of this. For example, we have this hardware here. It's an RF event detector. And what it does is it triggers the software whenever there's a radio signal present from your IoT device. So then you can go back in with the software and you can correlate exactly when is my radio turning on and off, exactly how much charge is that consuming from my battery, and is that where I want to put my design efforts? Is that what I need to try and tune up so that I can extend my battery life? We've also got several additional inputs with the N8705 that can trigger the software. For example, if you've got LED lights turning on and off, or you've got actuators or displays turning on and off, the software then will be able to look and tell you where that's happening so that you have a great idea for how often and how much charge each of your sub-circuits is pulling. So it gives you the insights you need to really help tune your IoT device design so that you can reduce the current draw and extend the battery life. Thanks for watching.